All right, so today we're taking a deep dive into large language models. You know those incredible AI systems that can write poems, translate languages, even code?
Oh yeah, they're amazing.
They are, but let's be honest, running them on your average computer,
Oh, it's a nightmare.
it's like trying to power a spaceship with a AA battery.
That's a pretty good analogy, actually. These LLMs are incredibly complex with billions of parameters. They just demand so much computing power.
So what if there's a way to make these AI powerhouses more accessible? Even if you don't have, a supercomputer in your basement, that's where the puzzle framework comes in.
The puzzle framework.
Yeah, and it's a method for optimizing LLMs to run efficiently on specific hardware, but without losing their magic?
Right, so it's like tailoring a high-performance race car engine, but you want it to fit in your everyday vehicle. You get the power and the performance, but it's optimized for your specific needs and resources.
I love that analogy. And we've got a stack of research papers and notes on Puzzle. It gets pretty deep into things like neural architecture search, knowledge distillation.
Oh, wow.
Yeah, but don't worry, we're going to break it all down for you. So whether you're prepping for like a tech meeting or just want to understand how AI is evolving, we got you covered.
So the main problem that Puzzle's trying to solve is this computational cost barrier of LLMs. Like imagine you want to build a chatbot, right?
Okay. Yeah.
But training a new, smaller LLM from scratch would take months. It would cost a fortune in computing resources. And then traditional knowledge distillation techniques, while useful, they're still very resource intensive.
So Puzzle's taking a different approach then. Like it's not building from scratch, right? It's optimizing what's already out there.
Exactly. Puzzle takes an existing LLM and, tailors its architecture to be more efficient on specific hardware. So it's not really about shrinking the model itself. It's more like streamlining its internal working so it uses resources way more effectively.
Okay, so how does Puzzle go about this optimization magic?
It's a really clever three-stage process. It's based on what's called a decomposed neural architecture search strategy, or NAS for short.
3 stages, huh? All right, let's break those down. What's the first step?
So the first stage is all about crafting those building blocks. Imagine taking a complex Lego structure and carefully separating it into all the individual bricks.
Okay, I can picture that.
That's basically what Puzzle does. It breaks down that big LLM to separate blocks. Then it uses a technique called Blockwise Local Distillation, or BLD. And it uses this to train these individual blocks, but in parallel.
Oh, parallel training. So it's happening simultaneously. That sounds a lot faster.
Exactly. And here's the cool part. Each of these blocks is trained to mimic the behavior of its corresponding block in the original larger LLM.
Oh, okay.
So what you end up with is this library of efficient block variants, and each one is optimized for a specific function.
So it's kind of like having a toolbox filled with specialized tools, right? Each one perfectly designed for a specific task.
Yeah, that's a great way to put it. Now, once you have all these awesome specialized building blocks, you have to assemble them into a new optimized architecture. And that's where stage two comes in. Puzzle uses something called mixed integer programming, or MIP.
MIP, that sounds pretty intense, like some serious math is happening there.
It is, but think of it like this. MIP is like a master architect evaluating all the different ways you can combine those Lego bricks, right, to build the most efficient and stable structure possible.
Oh, I see.
It considers, your specific hardware limitations, memory, throughput, latency, and chooses the best block combinations that maximize accuracy but stay within those constraints.
So it's finding that sweet spot between performance and efficiency, but we're not done yet, right? There's a third stage.
You got it. Stage three is all about uptraining. So this assembled model that we've made from all those carefully chosen blocks, it undergoes global knowledge distillation, or GKD.
GKD.
Yeah, think of this as the final fine-tuning step. The model is polished, refined, make sure everything works together seamlessly.
So like after assembling that Lego structure, you're making sure all the pieces are aligned and the whole thing's, rock solid.
Exactly. And what's really interesting is Puzzle actually goes a step further with something called decoupled BLD during that first stage. This significantly cuts down the computational cost of building that initial block library.
Decoupled BLD, what makes this so special?
Well, remember how we talked about training all those individual blocks in parallel? Decoupled BLD takes it another step. It actually trains different types of blocks, like the attention and FFN subblocks, independently first. Then, only after they're trained are they combined, instead of training every single combination from the start.
So streamlining the process by like training the individual components first and then figuring out the best fit later, that's pretty clever.
It is. It's kind of like figuring out what each Lego brick can do before trying to build every possible house with them. And this allows Puzzle to explore a much wider range of potential architectures, leading to even more efficient designs. So we've talked about the theory, but does Puzzle actually work in practice? Maybe we can look at a real-world example. So the researchers took this massive Llama 3.17 instruct model and used Puzzle to create a new model. It's called Nematron 51B.
Nematron, okay.
And get this,
Okay.
they actually achieved a 2.17x speedup running it on a single NVIDIA H100 GPU.
Wait, hold on. A 2.17x speedup. That's huge. But didn't they have to sacrifice accuracy to get that kind of performance boost? I mean, there's always a trade-off, right?
That's what's so remarkable. Nematron 51B retained 98.4% of the original model's capabilities.
Whoa.
It's actually the most accurate language model out there that can do inference on a single GPU with those large batch sizes.
Okay, I'm impressed. So that's having your cake and eating it too. That really drives home the point that Puzzle makes these LLMs so much more accessible. Imagine you could run this complex AI model on your laptop. So what really stood out to you about how Puzzle achieves this?
Well, for me, it's how the MIP solver isn't just blindly optimizing. It's like a master chef adjusting a recipe based on what ingredients are available.
Okay, I like that analogy.
So let's say you need a certain processing speed for your model. So a specific number of tokens processed per second.
Okay, let's say I'm building a chatbot and it needs to respond to like a bunch of users simultaneously. I need it to be lightning fast.
Exactly. So the MIP solver would take that into account, and then it would prioritize certain optimization techniques. So if you're really tight on memory, it might focus on reducing the size of the KV cache. That's kind of like short-term memory for processing.
Oh, okay.
But if speed is the priority, it might prune the FFN. That's the part of the model that does, a lot of the heavy lifting.
So it's like having a personal trainer for your LLM, you know? Customizing a workout based on your goals and limitations. And this completely changes how we think about, like, measuring LLM performance. It's not just about how big it is anymore.
You're absolutely right. For years, everyone focused on parameter count. Bigger is always better, right?
Right.
But Puzzle shows that inference performance on your actual hardware is what really matters for real-world applications.
It's like comparing, like, a giant truck to a nimble sports car.
Yeah.
Sure, the truck can haul a lot, but the sports car is going to win the race. And Puzzle highlights that, smarter optimization is the key.
Exactly. It's not brute force computation anymore. It's about finesse, tailoring the model to the specific task at hand.
Oh.
And that brings us to another fascinating aspect of Puzzle, scoring.
Scoring.
Yeah, so you mentioned different metrics used during this whole optimization process. You've got your downstream accuracy, language modeling loss, and KL divergence. What's the deal with all these scores?
Yeah, break those down for me.
Well, so downstream accuracy measures how well the model performs on specific tasks. So like answering questions or summarizing text. Then you've got language modeling loss. That assesses its ability to predict, the next word in a sequence, which indicates the overall quality of that language model.
Makes sense, okay.
And then you've got KL divergence. That one's a bit more complex.
KL divergence? Yeah, that sounds a little more in the weeds.
It is, but think of it like this. KL divergence measures how closely the output of like a specific block matches its counterpart in that original larger model.
Oh, okay.
It's like a similarity score. It shows you how much information is preserved during the whole optimization process.
So lower KL divergence means the optimized block is doing a better job of replicating the original model's capabilities.
Yeah, exactly. And what's really interesting is that KL divergence turned out to be like the best general purpose metric for optimization. It strikes a good balance between preserving accuracy and also achieving that efficiency. But the researchers didn't stop there. They actually also explored task-specific scoring.
Task-specific scoring. So you can actually tailor the optimization process to excel at a very specific task.
Precisely. So it's like training a dog, right?
Yeah.
You wouldn't use the same techniques for a guide dog and a sheepdog.
Right.
Similarly, if you need an LLM that's amazing at, writing code,
yeah,
you can fine-tune the optimization to prioritize that specific skill.
Wow, that opens up a whole world of possibilities. It's like building a Lego structure that's not only like super efficient, but also looks exactly like the picture on the box. And this points to a major shift in how we think about LLM development, right?
Absolutely.
There.
So Puzzle really challenges that traditional focus on parameter count and emphasizes like real-world performance under those specific hardware constraints. It's a much more practical and application-focused approach.
It's about time somebody said it. Size isn't everything. It's what you do with it that matters. So let's be realistic, though. No framework is perfect. What are some of the limitations of Puzzle?
Well, one limitation actually comes from that blockwise training approach. Remember, each block is trained individually,
Right.
which is super efficient, but it doesn't necessarily guarantee that they'll work together perfectly once they're assembled. It's like, those Lego bricks might not snap together as smoothly as you'd hope.
So there might be some hiccups in getting all those pieces to play nicely together.
That's right. Luckily, that final global knowledge distillation step helps smooth things out. But it's definitely something to keep in mind. And another limitation is the search space. So while Puzzle explores, a vast range of block combinations, there are still practical limits. There might be even more efficient architectures out there that haven't been discovered yet.
So even with all this clever optimization, there's always room for improvement.
Exactly. And let's not forget about the data. The quality and diversity of your training data will directly impact the accuracy of your model. It's like baking a cake. You can have the best recipe and the best tools, but if you're using bad ingredients, the cake's not going to taste good.
Garbage in, garbage out.
Right. So limitations aside, where do we go from here? What does the future hold for puzzle and LLM optimization?
Yep.
Well, the researchers have outlined some exciting directions they want to go in. They want to expand the search space further, incorporate new operations and architectural innovations. So imagine discovering entirely new types of Lego bricks that unlock even more creative possibilities.
Now you're talking. That's what gets me excited about AI, the constant push for innovation. What else are they looking at?
They're also exploring ways to optimize models for very specific capabilities. So things like chain of thought reasoning or multimodal tasks.
Chain of thought reasoning, multimodal, those sound pretty advanced. Break those down for me.
So chain of thought reasoning is all about teaching LLMs to think step by step like a human would, so that they can solve more complex problems. And then multimodal just means combining different types of data, like text and images, which is essential for tasks like, describing images or answering questions about them.
So we're talking about LLMs that can not only understand language, but also reason and interpret visual information. The possibilities are kind of mind-blowing.
They really are. But even with all these advancements, the researchers are always driving to improve the optimization process itself. So they're exploring even more advanced search algorithms beyond just MIP, like reinforcement learning or evolutionary approaches.
So using AI to build even more powerful and efficient AI.
Exactly. It's a fascinating feedback loop of innovation.
This has been an incredible deep dive, and I'm really feeling inspired by the potential of Puzzle to revolutionize how we use LLMs. It's not just about making models faster, it's about making them more accessible, more affordable, and ultimately more impactful.
I couldn't agree more. It's about empowering everyone to really harness the power of AI.
So what stands out to you as the most impactful aspect of Puzzle?
Well, without a doubt, it's the emphasis on real-world performance. We're moving away from these theoretical metrics and focusing on how these models actually perform on the hardware that people have, with all their real-world constraints.
Yeah, I loved that Nematron 51B example. They actually ran it on an NVIDIA H100 GPU, measured the actual performance, not just estimating based on some theoretical benchmark.
Exactly. And remember how the MIP solver can adapt to different needs. Like, if you need high throughput, it might prioritize techniques like FFN pruning. But if memory is your bottleneck, it focuses on reducing that KV cache size.
So it's like having a smart assistant that understands your specific hardware and tailors the LLM accordingly. And this challenges the whole obsession with parameter count, right, as the only measure of LLM performance.
Yeah, I'm glad someone finally said it. For too long, the focus has been on building bigger and bigger models, almost like an arms race.
Bigger isn't always better, right?
Exactly. Puzzle shows that a smaller, more optimized model can actually outperform a behemoth, especially when it comes to real-world efficiency. It's like having a precision tool versus a sledgehammer. Sometimes you just need finesse and control to get the job done right.
I love that analogy. And this shift in thinking, it has major implications for the future of AI development, right?
Absolutely. So instead of just chasing bigger parameter counts, we can start focusing on building more specialized models, designed for specific tasks and hardware.
Imagine a world where we have LLMs optimized for everything, from running on your phone to, like, powering complex scientific simulations.
And Puzzle is making that vision so much more achievable. It's about democratizing access to powerful AI.
So as hardware keeps evolving, do you think we'll see this, like, surge in these specialized LLM architectures? Each one optimized for, like, a particular niche?
I think it's inevitable.
Yeah.
As we move towards more edge computing and these personalized AI experiences, The demand for these tailored models is just going to skyrocket.
That's an exciting thought. It's like the Cambrian explosion of LLMs, each one perfectly adapted to its environment. But let's not get carried away with the future just yet. What are some things that developers need to consider when using Puzzle, like right now?
Well, first and foremost, you need access to the original parent model's weights. That's really the foundation for that whole optimization process.
Right, because Puzzle is all about refining an existing LLM, not creating a new one from scratch.
Exactly. And you also need to have a good understanding of your target hardware. So what are the limitations? What are your performance goals?
So it's not a one-size-fits-all solution. You need to really think about your specific needs.
Absolutely. And as we discussed, the choice of scoring metric is crucial. So KL divergence is a good starting point. But if you have a very specific task in mind, that task-specific scoring is definitely the way to go.
So it's about choosing the right tool for the job. What else should developers be aware of?
Well, let's not forget about the data, right? The quality and diversity of your training data, it will make or break your model's accuracy.
Right, garbage in, garbage out.
Exactly. And finally, it's important to remember that Puzzle, like any framework, has its limitations. It's not a magic bullet.
But it's a powerful tool that can significantly improve performance when it's used thoughtfully.
I completely agree. Puzzle is a huge step forward in making powerful AI more accessible and practical.
Well, this deep dive has been incredibly insightful, and I'm personally feeling very optimistic about the future of LLMs.
Me too. And it's important for our listeners to understand that this is just the beginning. We're just scratching the surface of what's possible with LLM optimization.
It's like we've opened the door to a whole new world of possibilities.
I couldn't have said it better myself.
Okay, we've covered a lot of ground today, so let's do a quick recap of the key takeaways before we wrap things up.
Sounds good to me.
So we started by highlighting the, elephant in the room. LLMs are incredible, but computationally expensive.
Yeah.
And traditional solutions like training from scratch or using existing knowledge distillation techniques, they're resource intensive. So Puzzle offers a much more efficient alternative.
Right, and we broke down the 3 stages of the puzzle framework. First, we have the crafting of those individual puzzle pieces, right, with Blockwise Local Distillation, BLD.
Then comes assembling the optimal LLM architecture using that mixed integer programming solver, or MIP.
And finally, that crucial uptraining phase with Global Knowledge Distillation, GKD, to really polish that model's performance.
We explored how Puzzle incorporates those smart techniques like decoupled BLD to streamline the optimization process, and how the MIP solver adapts to different hardware constraints and those different performance goals.
We also discussed that fascinating case study of Nemotron 51B, showcasing how Puzzle can achieve some significant speedups without sacrificing accuracy.
And we talked about how Puzzle shifts the focus away from just parameter count, emphasizing that real-world efficiency and task-specific optimization.
Of course, we acknowledge the limitations of Puzzle, right?
Yeah.
Emphasizing the need to carefully consider factors like, block compatibility, data quality, and even the choice of those scoring metrics.
But even with those limitations, Puzzle represents a major leap forward in LLM optimization.
It's a game changer.
Okay, so we've laid out all the pieces of the puzzle. Now, for the final part of our deep dive, we want to leave you with something to think about. A provocative thought that kind of builds on what we've discussed but wasn't explicitly addressed.
This should be good.
So here's the question. As hardware evolves and we see this potential explosion of specialized LLM architectures, what will this mean for the very process of AI development and deployment? Will we move away from these monolithic, one-size-fits-all models towards a more modular, plug-and-play approach?
That's a fantastic question.
Will we see the emergence of LLM app stores, where you can download and assemble pre-trained blocks optimized for, specific tasks and hardware? It's like building your own custom AI.
The possibilities are truly mind-boggling.
And if that happens, what impact will it have on, the accessibility and democratization of AI? Will it empower individuals and smaller organizations to leverage the power of LLMs in ways that we couldn't have imagined before?
These are all questions we encourage you to ponder, as you continue to explore this fascinating world of LLMs.
We hope this deep dive has sparked your curiosity and giving you a deeper understanding of all the amazing work being done to push the boundaries of AI.
And remember, the future of AI is not predetermined. It's being shaped right now by researchers, developers, and curious minds like you.
So keep exploring, keep questioning, and keep pushing the limits of what's possible.
We'll be right here with you every step of the way, diving deep into the most exciting developments in AI.
Thanks for joining us on the deep dive.
Yeah, that's a really powerful thought to leave our listeners with. It really highlights how puzzles' impact goes way beyond just the technical innovation.
Absolutely. It's about making these AI tools, more accessible to everyone. It's about shifting the focus away from these massive corporations, the ones with like unlimited resources, and giving power to individuals, researchers, smaller organizations. They can bring fresh perspectives and ideas to the table. I love that. Imagine a world where, you don't need a supercomputer to run these advanced models. You can have an AI assistant tailored to you, your needs, running smoothly on your own devices.
Think about it. Personalized AI tutors that adapt to your learning style. Smart assistants that truly understand you, your needs. Creative tools that unlock new avenues for, like self-expression.
So many possibilities, but with this potential, there's a lot of responsibility, right? As we make AI more accessible, it's even more important to make sure it's used ethically, responsibly.
Oh, 100%.
Yeah.
We need to be having those open and honest conversations about the potential risks and challenges of AI. We need to work together to develop guidelines and frameworks that make sure it benefits all of humanity, not just a select few.
It's like giving everyone this powerful tool, but not giving them the instructions or the safety precautions.
Yeah, exactly. We can't just be focused on the technical advancements and forget about the bigger picture, you know, societal impact. AI development has to be approached responsibly, with a purpose, to make sure it's contributing to a better future for everyone.
And that's where you come in, our listeners. Stay informed, ask those questions, engage in those critical conversations about the future of AI. Your voices are crucial.
The future of AI, it's not being dictated to us. We're shaping it together right now.
Such a powerful message. This deep dive has been incredible, just a really amazing journey into the world of LLM optimization. I hope everyone feels, inspired and a bit more knowledgeable.
And remember, this quest for efficient, accessible AI, it's ongoing. Brilliant minds all over the world are pushing the boundaries of what's possible.
We'll be here, diving deep into those latest developments and bringing you the insights you need to navigate this crazy world of AI.
Thanks for joining us on the deep dive. Keep exploring, keep learning, and most importantly, keep asking those thought-provoking questions.
Until next time, keep diving deep.